Okay, last time we talked about some ancient history, what we would call cosmology. Cosmology is the study of the universe. Talked about Ptolemy, who said that the Earth was a sphere, everything revolved around it, and the planets were the wild cards, the wanderers. In fact, I did say it in the last video, I was running out of time, but if it hadn't been for the planets, we probably would still believe what Ptolemy said because it so perfectly models what's happening. But the planets caused a problem and they had to be figured out. And if you had to use perfect circles on top of circles, you end up with something that models it, but not perfectly. So Copernicus came along, changed the model, put it as heliocentric, but the problem there was if you have perfect circles, even the heliocentric view doesn't work. It isn't until you come along to Johannes Kepler and his three laws. Sir Isaac Newton took what Kepler did and came up with what is known as the universal law of gravitation. Now, let me explain that. It's a law, so it predicts. It's universal because we believe it applies to all massive objects in the universe. Gravity is a force between objects that have mass. It doesn't matter if it's a planet like the Earth or an atom. There is a gravitational force or pull between any two objects. Now, this is the way Newton figured this out. Newton knew his three laws of mechanics. He knew that a force always produces an acceleration in the direction of the force. And he also knew that for every force there was an equal and opposite force. And Newton also knew that there is a force called the centripetal force, which is m4 pi squared r over t squared. If you want to know what the force on something is, we need to know what its radius is, what its period is, what the mass is. Newton looked at Kepler's law, which said if I put the sun there and then we take Mercury and Venus and the Earth and Mars and way out here Jupiter, and we take and we find what is this distance, r, what is the period, that r, the period squared divided by r cubed is always the same number. Now that's only true for the planets in the solar system. That's not true for instance, well, let's just leave it at that. It's true for the planets in the solar system. And Newton looked at this and he said, okay, this is the mass of the planet. And I've got 4 pi squared r over t squared. But now look, t squared, and by the way, even though it's technically ellipses, that makes the math a ton more complicated. We're going to pretend the orbits are circles because they almost are. If I redo this, t squared is equal to kr cubed, which means that I can take this equation for the planets and put 4 pi squared r over kr cubed. Or centripetal force on the planets is the mass of the planet. And I'm going to pull this out here, 4 pi squared over k times 1 over r squared. Now Newton looked at this and he said, okay, 4 pi squared times the constant, this is a constant. 4 pi squared over k is itself a constant. I'm going to write it as a big K. So I could now rewrite this. Fc is equal to the mass of the planet times big K over r squared. But then he asked himself a question. What is it that is common to all of these planets? And the answer is they all are being attracted by the sun. And so he replaced this K with a new constant G times the mass of the sun. MS stands for the mass of the sun. This G is known as the universal gravitational constant. And now I can rewrite Newton's equation for centripetal force like this. The centripetal force on a planet is equal to, well, I'm going to do it this way first, mp times g times ms over r squared, or fc is equal to g times mp times ms over r squared. And that becomes the universal law of gravitation. What the universal law of gravitation tells us is that if I know the universal law of gravitation and I want to know what the force is between two objects, I simply have to know how far apart they are and what their masses are. You need the two masses and you need r squared. And by the way, r squared is from the center of mass for most objects. So for instance, when we stand on the earth, we take, and we're standing right here on the earth, the distance between you and the center of the earth is what r is. If you were standing right next to somebody, and in fact, let's say that you were hugging somebody, your distance is not zero, or this would be infinite. The distance is between your centers of mass. So let's say we have a person here, and that's kind of a weird person, but right here, and do this. Well, the distance is probably close to 0.5 meters or something like that, because we're about, however far from here to here, 25 centimeters maybe. The point is this number never goes to zero. Now, this law applies to everybody and everything. So I can generalize this once more, and I'm now going to just call this F. We're going to put G here, and we're going to put M1, M2 over R squared. As soon now as we know what G is, we will be able to figure out the force of attraction between any two objects, including planets and the sun and the moon and anything else. The man who gets credit for finding G is a man by the name of Henry Cavendish. And he did a really cool experiment about 100 years, if I remember right, after Newton, but it might be a little off from that. What he did was he took a very thin rod, actually a piece of wire, and on this wire he put a little piece of a mirror, and he shone a light at that mirror. And of course that bounced off onto a screen. And then he took and he put a great big bowling ball here and a great big bowling ball the same distance there. And according to Newton's law of gravity, these two should attract each other, and they did, and they moved toward each other, and as a result this beam of light shifted. And by knowing what the torsion is, how hard it is to twist it, he was able to calculate how much force had been put on that wire. And then knowing the distances between these, he was able then to come up with the universal law of gravitation. The universal law of gravitation, G, is 6.67 times 10 to the negative 19 newtons meters squared per kilogram squared. And let me just make sure. Oh, not 10 to the 19, I'm sorry, 10 to the negative 11. All right. It's a very, very, very tiny number. It's so tiny that we totally ignore the gravitational effects on anything like when you have people. But let's say that we had two people. Let's say you were a 100 kilograms, so about 220 pounds if you remember. Let's have somebody else be 80 kilograms, and let's say that they are 0.75 meters apart, so they're actually fairly close. What's the force of gravity between them? Well, it's 6.67 times 10 to the negative 11 times 100 kilograms times 80 kilograms times divided by 0.75 meters. And by the way, you have to square it. If you don't square it, you'll end up coming up with the wrong answer. And I'm not going to work it out because I don't have my calculator, but you can just plug that in. Turns out to be incredibly tiny. Even if we say this is 100, this ends up being times 10 to the negative 7. So this is going to be in the range of approximately 10 to the negative 7 newtons, or 1 times 1/1,000,000th of a newton, which would be so small you would hardly be able to even notice it. And that's why you can't just scale things up. I mean, I've had students say, well, why don't little bugs get trapped in orbit around a fat person? Well, if you take a fat person, let's just take somebody who's 1,000 pounds. They also happen to be fairly wide. The center of mass goes to, say, 1.5 meters. And the little bug has almost no mass. Let's say he's 0.01 kilogram. And you put that in, and the force on that bug is so tiny that it's insignificant. This is, though, a fantastic discovery, because it explains that throughout the entire universe there are forces which are holding massive objects together. It's the reason galaxies form. It's the reason planets form. It's why gas clouds condense down into stars and so on. What's even more interesting, and this lesson will be quite a bit shorter than the last one because the equation is pretty much the same. I mean, pretty easy to work with. But once we know what G is, we can then find the mass of every object in our solar system. In fact, Cavendish is known as the man who weighed the Earth. So you say, well, how in the world is that possible? Well, let's just look at it. The force of attraction between you and the Earth, I'm going to use E for Earth divided by R squared. This force of attraction is m1g. And m1 here will cancel out. So G, which we happen to know, is pretty obvious. R squared, we know what that is. That's the radius of the Earth, and that's a fairly well-known number. And so by rearranging this, G R squared over this, we get the mass of the Earth. Mass of the Earth. I have the numbers for that, but they're also in your book. I actually don't need to put those down. We just have to know the radius. It's like 6.4 times 10 to the, I forget what it is now, the radius times 10 to the 3 or 4 meters, more than that, kilometers, divided by G times little g. G here is 9.8 meters per second squared. And then once you know the mass of the Earth, then you can do something like this. The mass, the force on the Earth is G times m(e) ms over r squared, where this is the mass of the sun. Notice what happens. This is the centripetal acceleration. So this is the mass of the Earth times the centripetal acceleration of the Earth. And that we can calculate really easily. It's how fast, just knowing how long it takes for the Earth to go around once, we can figure out what the centripetal acceleration is. And boom, we've got the same thing. The centripetal acceleration, which is easy to measure, gives me the mass of the sun. And then once we know the mass of the sun and the period of the planet, we can then work backwards to what's the distance between them and what the mass of every planet is. So it's actually a pretty amazing discovery. Now, one last thing, and I need to just point this out. We now have 3 field forces. The first one you got introduced to was electricity. K, Q1, Q2 over R squared. And then we had F is equal to B times, and I've just gone blank on what we use for magnets. It's, well, that's terrible. The magnetic field, it's not Q, but over R squared. I'll get it in a second. And Q, M1, M2 over R squared. Sorry about that. That's really bizarre, but my mind just went blank on what we used for the for magnetism back in 24, chapter 24. Yeah, I'm going to have to, but I'm not going to worry about it. We'll just call this x and x. It's not x, but that's what it is. But notice how similar all these equations look. There's a universal constant. They have exactly the same form. They're inverse square laws, and they are very, very similar. The difference is that gravity is always attractive, whereas these one can be attractive or repulsive. And the other is the size of these. Q is times 10 to the negative 11. This is times 10 to the 19th. And B is also a very, very large number. And so there's a similarity there, but there's also some differences. So you're going to be asked to do some problems out of this section. This is chapter 7. I'm going to do problems 24, 27, 31, 42, 55, 57, 63, and 65. Just to get you familiar with that equation and also the inverse square part. It is an inverse square law, which means that if you double the distance, you cut the force down to 1/4 of what it was before. So, all right, and with that, we'll quit. We have one more lesson, some applications of Newton's universal law of gravitation.